This is optics lesson number 2, looking at the beginnings of refraction and reflection, and looking at reflection specifically in plane mirrors. So starting out, okay, light moves from a source outwards in all directions and moves in the form of a wave. And though it moves in a wave, the wave itself moves in straight lines. So we often will show rays of light not as waves, but as a straight line with an arrow. So here, light is emitted from a bulb in all directions. It travels through the air like a wave. But as it travels through the air, it does so in straight lines. So when we draw a ray of light, we draw it as a straight line with an arrow on the end. Usually, we would use a ruler. Really, you should be using a ruler. So there are different ways that light can pass through different surfaces and be reflected or transmitted through the different substances. So the first thing that light can do when it hits a surface is it can be reflected. So reflection, okay, is when the light bounces off of something. So bounces off the material. So let's say we have something metallic, like a mirror or a pan. Okay, so this is our surface. And the light's going to come in and it's going to go out again. So when it bounces off of a surface. Versus the second type of thing that it can do is it can be transmitted through whatever the material is. So transmission okay, the light passes through. The material. Okay, so refraction is the bending of light when it passes through something. So you can kind of see it in this picture here. We've got a beam of light coming in. When it hits the glass, it's not going straight through, it's bending at a bit of an angle. And then again, when it leaves the glass, it's bending a second time because it's switching from different densities of materials. So from glass to air and air to glass. We're going to spend the second half of our unit looking at refraction. So that will be after the weekend. But for the first couple days, we're going to focus on reflection. Ray diagrams, there are some important rules that we need to follow and understand about them before we start drawing lots of ray diagrams. So first of all, a ray diagram shows the movement of light from a source. So if you have a light bulb or a fire or something, the ray diagram, so the line with the arrow is going to show in what direction the light is traveling. Okay, the behavior of the light when it hits a material, or passes from one material, or we call them mediums, to another, okay, are represented using these ray diagrams. So we use them to show how the light is going to interact with the surface. Okay, so we use an arrow to represent the movement and the direction. Okay, and always use a ruler. So I'm just going to make a note. Use a ruler. So for this unit, you are going to need a calculator and a ruler most of the time. Great. So I keep going with our ray diagram terminology here. So here we have a ray in red with an arrow showing the direction and movement of light. It's going to hit a surface. So here we have a shiny surface, and it's going to bounce off when it's reflected by this shiny surface. Now there's a green dashed line down the center here called the normal. So the normal is a line drawn perpendicularly to the surface. At the spot where the incident ray, so the ray that's coming in, touches the surface. So I'm going to even add a little note here. At the spot, so it's a line perpendicular to the surface at the spot where the incident ray touches the surface of whatever the material is. So in our ray diagram here, there's our normal line. It's just an imaginary line that we use to help us measure the angles of the different rays. So your incident ray, we call this just sort of I. Usually you would just give it an I symbol. Okay, so the incident ray is the incoming ray. I think there's only one M in incoming. Sorry. Is the incoming ray. The angle of incidence which has the symbol theta with a lowercase I. Okay, so symbol, the ray gets an I, and the angle of incidence gets a theta I. Okay, is the angle between the incident ray and the normal line. So you'll see in this diagram, the angle of incidence here is between the incident ray and the normal. The biggest mistake that people make is they measure the angle of incidence between the incident ray and the surface that it's touching, but we need to always make sure it's between the normal, and the incident ray should always be in there. For the reflected ray, we call them R, okay? And the angle of reflection is theta with a lowercase r. Okay, is the outgoing ray after the incident ray has touched the surface. Okay, the angle of reflection theta r, is the angle made between the reflected ray and the normal line. Okay, so here it is here. Theta r is between the reflected ray and the normal. So let's try a practice question of a ray diagram. Label the incident ray, the normal on the diagram. So we'll start with that. This is our incident ray, and this is normal. So incident ray is our incoming ray with an arrow on it. Normal is a dashed imaginary line at the point where the incident ray touches the mirror perpendicular to the mirror surface. Draw in the approximate reflected ray, so where you think roughly it would go. You don't have to measure with a protractor. Just give an estimate. Okay, and remember, if it's a ray, it needs to have an arrow on it. Label that R for our reflected ray. Label the angle of incidence and the angle of reflection. So here we'll label this as theta I, and here we'll label this as theta R. Now this isn't a perfect diagram because those don't look the same, but ideally they should be about the same. So our rules with with mirrors. Okay, so this is called the law of reflection. So the angle of reflection is equal to the angle of incidence. Okay, so your theta I should always be equal to theta R. What that means is if you have a flat surface, all of your normal lines are going to line up with each other. Okay, your angle of incidence and your angle of reflection are equal, and all of the rays of light that are bouncing off a surface are going in the same direction. So you're going to get a nice clear picture, okay, like if you were to look in a mirror. Versus if you have a rough surface, okay, you'll notice if you were to draw all the normal lines on here, okay, they would be all over the place. So they wouldn't be equal to each other. They would be kind of all over. And your reflected rays are going to be all over the place as well, which means this is when we get something that's either not very reflective or it produces a very blurry image. Okay, so here we have regular reflection. Okay, when you have your normals lining up on a nice flat smooth surface. And when you have a rough surface, okay, this is when we get something called diffuse reflection. Okay, and an example of this would be like if you were looking out at a lake. Okay, in the morning when it's super, super quiet and smooth, you would get regular reflection. Okay, where the picture, the image in the lake looks exactly like how it is above. But diffuse reflection might happen later in the day when it gets windier and the water becomes all choppy and it's not a smooth surface anymore. And then the reflection in the water is then very blurry and you can't really see anything clearly. So reflection in plane mirrors shows regular reflection. In a plane mirror, okay, it's usually a very flat surface. This is like the type of mirror that you would use when you're getting ready in the morning and you're brushing your hair or your teeth or something like that. Okay, but as you may have noticed in previous experiences that when you look in the mirror, if you're wearing, say, a shirt with a logo on it, with letters on it, that there is actually a lateral inversion to any image in a plane mirror. So a lateral inversion means that the images in the mirror are always reversed left to right or flipped left to right. So it's important if you ever want to, write something on your face, like, go Leafs or something, have somebody else do it for you. Don't try it and do it in the mirror because you'll end up writing it backwards. So images in plane mirrors, if you're trying to find any image in a plane mirror, okay, we usually always want to have sort of 3 lines of evidence. It's similar to writing an essay. So if you were to write an essay, you want to have 3 lines of evidence that support your thesis. When we're doing ray diagrams of any kind, so we're going to do a whole bunch over the course of this unit, different types, you always want to have 3 sort of lines of evidence to show that where you predict your image is going to be is actually somewhere that you've sort of proven that that's where it will show up. So here we have a line where it's going to hit the mirror directly straight on, and it's going to be reflected back out with an angle of incidence of basically 0. So it's hitting perpendicularly, it's right on top of the normal. So the reflected ray is coming straight back. If you were to do a couple other angles, okay, you would send your light ray in, it would hit the mirror. Here your angle of incidence will equal your angle of reflection, and you would get your reflected ray coming off. Same with the bottom one, so another angle of incidence equal to the angle of reflection. Okay, and then that would be your reflected ray coming off. Your image will always be found where your reflected rays intersect. So in this particular case, if you were to ignore the backside of the mirror, you would see that all of your rays will never touch each other on the real world side of the mirror. Okay, so this line, this reflected line, and this reflected ray are never going to meet over here. But if we extend them backwards into the mirror, they will intersect, and that is where that spot of your object will appear. Which is why when you look in the mirror, it looks like your reflection is inside the mirror, like it's behind the mirror. So characterizing images. We always want to characterize all of our images in all types of ray diagrams using mirrors and lenses and curved mirrors, flat mirrors, and there's specific terminology that we use to classify these. So you can make an acronym out of it. You can sort of think of it as like step 1, 2, 3, 4, whatever you want to do. But there's 4 main things that you need to talk about. And so the first thing is type. You always need to say what type it is. The second thing is orientation. And then the third and fourth are height and distance, which can be combined into magnification. So this is sort of 3 and 4 is your magnification. So let's start with type. There are 2 types of images. Okay, there are real images and there are virtual images. So real images are things where real rays of light actually intersect with each other. So the intersection of real rays, okay, images can be captured, okay, on a screen in front of the mirror. So this would be like if you were using a curved mirror to produce like a projector. Okay, so some projectors use mirrors. The ones that we have in school that kind of come out from the top of the board. So like if you had this is your whiteboard, and then we have these things that come out, and then there's a projector that drops down here and shines it out this way, and then there's a special mirror that sends the image out here, and you can actually capture it on a screen. Versus if you were to put a screen in front of a regular plain mirror, right, you wouldn't see a projected image of yourself on that screen. Your reflection only exists within the mirror. So that's what virtual is. So a virtual image, okay, is an intersection of virtual rays, okay, that don't actually exist as real light. Okay, these images cannot be captured on a screen, okay, because they're in the mirror, okay, it's in the mirror. So to help you kind of know what that means, real rays are always solid lines in ray diagrams, versus virtual rays are dashed lines. Okay, real rays are in front, okay, of the mirror, and dashed rays are behind the mirror. So that's the first thing. Orientation has to do with whether it's the same way up or not. So orientation, we have 2 classifications. They can be upright, which means that your image and your object are both in the same vertical orientation. So they would both be like up and up. So this would be like your image and your object would be the same. Versus inverted, okay, is the other option, which is basically upside down. So your object, okay, is up, but then your image is upside down. So it's flipped top to bottom. Now, size and magnification has sort of 2 categories, but these are between height and distance, and they're very, very closely related. So we can talk about them kind of as one thing, as magnification, and that's what we'll do for most of our stuff with mirrors, but we'll get into a little bit more detail when we talk about lenses in terms of splitting those 2 things apart. So first of all, okay, the ratio of the height of the image to the height of the object can give us the magnification. So the height of the image, so this is HI, to the height of the object, HO, will give us an idea of whether the magnification is smaller, equal to, or larger than the object. Okay, so we can say that our image is smaller than the object if m is less than 1. It can be equal to, okay, so it can be the same. Our image can be the same as the object. In that case, your magnification is equal to 1. Or your image can be larger than the object, in which case your magnification is greater than 1. So less than 1, equal to 1, and greater than 1. Okay, and this just has to do with exactly how big your image is. So if it's smaller, okay, your image is going to be smaller than your object. If it's equal, you've got an image and an object of the same size. And if your image is larger, then your magnification is greater than 1. And this also corresponds to distance. So any image that is smaller will also be closer to the mirror. Any image that is larger will also be farther away from the mirror. And anything that is the same height will be the same distance. So here, this diagram sort of shows you height of the object versus height of the image. Distance of the object is measured between the object and the surface of the mirror. Okay, and then object and surface of the mirror. So distance between the object and the mirror, okay, is your DO, and the distance between the image and the mirror is your DI. So when you look in a plane mirror, think about what are the characteristics of your image in that plane mirror. Okay, so the type might be a little bit hard for you to think about right now, but think back to our image that we looked at on this page, okay, in a plane mirror. Are these real rays of light that are connecting to form an image, or are they virtual rays of light that are connecting to form an image? In this case, the rays are dashed and they're behind the surface of the mirror. So images in plane mirrors will always, okay, be virtual. It doesn't matter how close or how far the object is from the mirror, they'll always be virtual. Orientation for a plane mirror, okay, if you look at yourself in a plane mirror, you'll always be the same way up. Okay, you're never going to be flipped, so the orientation will always be upright. And finally, your magnification. Okay, if you look at yourself in a plane mirror, you'll find that you are the same size in your image as you are in real life. And if you move closer, you look a little bit bigger. If you move further away, you look a bit smaller. So in this case, your magnification is equal to 1. Okay, so what this means is the height of the image will be equal to the height of the object. Okay, and the distance of the image will be equal to the distance of the object. So if you move closer to the mirror, your image moves closer to the mirror. If you move further away, your image moves further away as well. Okay, so for plane mirrors, regardless of how close or how far you are from the mirror, you will always get the same characteristics of your image. In curved mirrors, it's a little bit different, but we'll get to that tomorrow. So for your to-dos, on page 11, you have some practice questions. So this is review from the first lesson. Then you've got a ray diagram and a few questions about ray diagrams and reflection in plane mirrors. When you're done, take a picture and submit it to Etsby.